the z-axis slide is moved so that the reflector and interferometer are at their minimum distance of separation. That is, the z-axis slide is jogged to the z=0 position. With the z-axis slide at 0, the position of the laser beam is adjusted until it passes through the 3 mm hole in the target. This adjustment can be made by adjusting the position of the x-axis slide on which the interferometer rests, or by adjusting the position of the laser head using the tripod's angular and translational adjustments. Remove the target from the interferometer and note the position of the returning laser beam with respect to the return port on the bottom of the laser head. The position of the reflector must be adjusted until the returning laser beam is centered on the return port's crosshairs. This is referred to as establishing the near end of travel. To align the laser beam with the axis of travel, a target is placed on one of the retroreflectors of the angular reflector. The target is positioned so that its crosshairs are centered on the laser beam. Another target is placed on the entry-exit port of the angular interferometer such that its hole is centered around the laser beam. The reflector is moved away from the interferometer by jogging the z-axis slide in the positive direction. Observe that the red laser beam spot has moved away from the center of the crosshairs on the reflector target. When the spot has nearly moved off the target, jogging is stopped. Using the tripod adjustments, the laser head is rotated in the horizontal and/or vertical planes to bring the laser beam to the center of the reflector target crosshairs. Notice that the laser beam is now blocked by the target on the interferometer. With the tripod adjustments, the laser head is translated in the horizontal and/or vertical planes to bring the laser beam to the center of the hole in the interferometer target. If the beam is no longer centered on the reflector target's crosshairs, the laser head is again rotated with the tripod adjustments until the beam is centered on the reflector target's crosshairs. If necessary, the laser head is again translated until the beam is centered with the hole in the interferometer's target. The z-axis carriage is once again jogged away from the interferometer until either the beam nearly moves off the reflector target or the end of travel is reached. When the beam moves away from the center of the reflector target crosshairs, the previously described rotation and translation steps must be repeated. Once the end of travel is reached, with the beam being centered on both targets, the alignment is complete. As the z-axis carriage is jogged back to the point of minimum separation of the optics, that is z=0, the strength of the beam being received at the laser head's return port is monitored. The needle on the beam strength indicator must stay in the green area during the full range of z-axis travel. In the event that the needle does move out of the green zone, the alignment of the laser beam with the axis of motion is not satisfactory, and the alignment process must be repeated. Once the alignment has been verified, the sign convention of the measurements must be established, and the physical nature of the measured angles must be understood. An easy method for this can be described as follows. Zero the measurement display by pressing the reset key. Lightly press on one side of the reflector and note the sign of the angle change. It's a good practice to record this relationship or even to make a sketch of the sign convention. The sign of the measured angles can be reversed by pressing the direction sense key on the measurement display. If you do change the sign convention, be certain that you understand the conditions that you have selected. To begin a measurement, the measurement display is reset to 0 with the reflector and interferometer at their minimum separation distance. In this case, that correlates to a z-axis position of z=0. The DTM is programmed to move the z-axis carriage from z=0 to z=150 millimeters in 25 millimeter steps. A 5-second pause between steps has been included to allow time for the carriage vibrations to diminish and the measurement display to stabilize. 0, the yaw angle reading for z=0, is recorded. At each 25 millimeter interval, the yaw angle is manually read and recorded. To obtain more representative data, the yaw angles are also read at each interval as the z-axis carriage returns to z equals 0. This technique also allows a check of hysteresis and thermal effects which might be present in the operation of the carriage. In the event of non-closure, where the ending point fails to coincide with the starting point, the validity of the gathered data could be suspect. To change the setup for pitch measurement, the reflector and interferometer would be reoriented vertically as shown. In this lab, we have demonstrated yaw measurement with an angular interferometer system. We have discussed how the angular interferometer and reflector use two measurement beams to sense the rotation of the moving reflector. We showed the setup of the hardware and discussed a method for data collection. Like straightness of motion data, yaw measurement data can be used to estimate workpiece errors as well as to provide data for error compensation routines. The homework assignment for this lab involves the interpretation of yaw angle measurement data. The following data represent three sets of yaw measurements for the z-axis carriage of this DTM. For each set of data, the yaw angle for the z-axis carriage is measured at 25 millimeter intervals along the axis of travel, starting at z equals 0, traversing to z equal 150 millimeters, and then returning to z equals 0. The sign conventions for the machine axis and the collected data are identical to those presented in the laboratory demonstration. Plot the results of the three sets of data on a common graph and comment on the repeatability of the data, and so forth. Sketch the machine axes and indicate the direction of the yaw angle. The lab write-up should follow the standard format consisting of the objective, procedure, results, and conclusion. The write-ups must be typewritten or legibly handwritten. These write-ups are due at the beginning of the next lab.